Okay, we've got a little bit of experience playing with a kitchen funnel and various different liquids to see how quickly they come out of the funnel. And we filled it up full, then let it start flowing out of the funnel till it got to some line that we marked as being empty before the bottom of the funnel started to empty out. And I think the funnel that I used was about these dimensions, about a 7mm inside diameter here, maybe about 3 centimeters on the narrow portion here, an overall height about 7 centimeters. And I think, and I'm just guessing, but I think I managed to get about 250 milliliters, about a quarter of a cup of fluid in between that empty line and the full line. Now the question we have to ask ourselves if we want to do any analysis of this, to understand why we got the kinds of results we did, we'll have to figure out what forces are important in generating this data that we actually measured, because this is a reasonable representation of what actually happened. So as the kinematic viscosity increased, the time that it took for stuff to come out of the funnel increased. And in my case, I got something that looked like it might have been a linear variation. It's hard to tell because I'm really uncertain about where on the viscosity line that data point really belongs. So I put an error bar on this of about that big. So it could be linear, it might not be linear. It really depends on the properties of this fluid. This is hot dish soap, this is hot dish soap, and this is cold room temperature dish soap. One thing to notice is as we come down here, as we get down to this point here, this point is canola oil. It took 10 seconds to come out of the funnel. It's got a viscosity of around 0.0001 meters squared per second. And this is time in seconds. So about a tenth of the dish soap viscosity, and it took about a quarter of the length of time to come out. And yet water, far, far lower viscosity, and even hot water, far, far lower viscosity, only took a little bit less than 10 seconds to come out. So something seems to be changing down in here. And maybe if we look at the forces, look at the dimensionless groups, we can start to understand that. So what forces are important? For sure, gravity. Gravity forces are definitely going to be important because that's what's causing the fluid to flow down out of the funnel. That's what pulls it down the funnel. We have a strong indicator that viscous forces are important because viscosity is playing a major role here. Big viscosity, long time. Small viscosity, short time. Definitely viscous forces are involved. Are there any other forces that are involved? The fluid starts out here, it's going, well, it's hardly moving at all up here at the full line. By the time it comes out the bottom, it could be going quite fast. We could be just translating the potential energy of this fluid into velocity down here. Even if the fluid was very, very low viscosity, it would still take some time to flow out of the funnel. So the velocity may be important. So inertial forces are going to be important. Now we have a dimensionless group that allows us to compare gravity forces with inertial forces. We have another dimensionless group that allows us to compare viscous forces with inertial forces. Gravity forces compared with inertial forces, that's the Freud number, Fr, and it's equal to the velocity, some characteristic velocity, divided by the square root of the acceleration due to gravity and some length scale, some appropriate length scale for the flow. Likewise, for viscous forces, we have the Reynolds number, which is equal to some characteristic velocity times some characteristic length scale divided by the kinematic viscosity. Now remember, kinematic viscosity is equal by definition to the absolute or dynamic viscosity divided by the density. And this ratio comes up so often when we're trying to compare viscous forces and forces associated with the mass that we've actually defined a separate value for it, and it's the one that we're probably looking at in this instance, because we're interested in how viscous is it compared to how much gravitational force comes from the mass. So viscous shear stress in the dynamic viscosity divided by mass force downwards due to gravity represented by density here. So these two dimensionless groups should be important. But what should we use for u as a representative velocity? We didn't measure velocity. We only measured time. How can we get an appropriate velocity? Well, the flow coming out of this funnel, it comes out at some average velocity on the way from full to empty. It starts out being fast when it's full, and it's not as fast when it's almost empty, but we could take some kind of an average over time. And in fact, it's probably going slower over here by the walls of this little pipe than it is in the middle. But if we wanted to get an average over the cross-section of the funnel and an average over time, we could just take the total amount of volume of fluid that passes through the tube and divide it by the cross-sectional area of the tube. Because the smaller the tube, the faster it has to go to get this much volume through here in a given amount of time. So let's take an average, and that'll be our characteristic velocity. And it'll be the amount of volume that we had in the funnel divided by the time it takes for that volume to get out of the funnel. That'll give us a flow rate in cubic meters per second. And if we then divide again by the area, the cross-sectional area of the exit here, that'll give us an average velocity in meters per second. So let's make sure that we get our dimensions right. That'll be, the volume is 250 milliliters. That's a quarter of a liter, and a liter is 1,000th of a cubic meter. So if we want this in cubic meters, it'll be 250 milliliters times 1,000 milliliters to a liter and 1,000 liters to a cubic meter. So times 10 to the minus 6 is the volume in cubic meters, divided by the time, so times 1 over t, and divided by the cross-sectional area. Well, that'll be pi times the diameter squared. If it's 7 millimeters inside diameter, that'll be 7 times 10 to the minus 3 meters squared divided by 4. Right? Pi d squared over 4 is the cross-sectional area of a circle, times 1 over t. That'll give us our average velocity. And if I punch all of those numbers together, that's going to give me an average velocity equal to 6.5 divided by t. So that'll give me a characteristic velocity.